Hello everyone. RMO happened day before yesterday and the question paper is available online. We are going to discuss my own perspective of the first problem. This is a problem from non-KV, non-JNB paper. This problem does not require any theoretical knowledge. It just needs some pattern recognition. And I really appreciate this problem and I'm also impressed about the type of questions that are now appearing in the exams. Let's take a look at the part A of the first problem. Over here you have two subdivisions. So partial marks are always available. You are given with n lines on the plane. You have to find configurations of those n lines in order to have n minus 1 distinct intersections of them. For example, you take 5 lines that must render 4 intersections that are distinct. And we assume the number of lines greater than or equal to 3 for both these cases. So when you talk about lines and their configurations in the plane, two things comes to my mind. First, parallel lines. Parallel lines make no intersections. So however large you extend on either side, you are not going to get intersections. If they are not parallel, they will exactly have one intersection. Maybe quite far, but they will eventually intersect. So the intersection and non-intersection should just depend on whether they are parallel or not. Secondly, sharing common intersection. That's when you have concurrency. So a diagram like this minimizes the number of intersections by accumulating over a point. And if you consider parallel lines, they also minimize the number of intersection in some other sense. Now, using some of these configurations, maybe you are required to design n lines with n minus 1 intersections. Let us suppose consider n minus 1 lines that are mutually parallel, like this. And the nth line intersects all of them by being not parallel to these set of parallel lines. You see, there are n minus 1 of them. There are n minus 1 of them. And this is the nth line, just only one line, that intersects all these n minus 1 parallel lines, thus creating n minus 1 distinct intersections. Of course, they are not coincidental. They have some space in between them, making these intersections distinct. Probably this is easier configuration to guess. But while you come with n intersections for the same n lines, how are you going to deform this shape or configuration to obtain that one extra intersection? Might as well you can take some time to think on it. Or if you're not with any ideas, we particularly assumed all these lines to be non-intersecting because they are parallel mutually. What if all of them converge to a particular point? Then they induce concurrent lines. Let's draw that. I'm going to. So they are all converging to a point, and you have that one extra line intersecting these n minus 1 other lines. Clearly, these n minus 1 intersections will be quite similar to the earlier case, but this concurrency creates one extra point of intersection. Therefore, there are total n intersections. So in this sense, I think just the pattern recognition skills plays crucial role rather than some conceptual knowledge. If you do a lot of projective geometry, these kind of configurations would be naturally occurring in your mind. Okay, let's go to the part B. This is about particular values, and actually it's n plus 1. So they gave particular values because it's not easy to generalize. For n intersections and n minus 1, that was easy. And here you have 8 lines with 9 intersections. So you need a lot of intersections. And one possible configuration that I was able to come up with is the following. Suppose you have 3 parallel lines that are uniformly spaced, and horizontally you have 3 parallel lines. Again, uniformly spaced. These constitutes 6 of these 8 lines. But already I have reached 9 intersections. I have exhausted all my intersections. Yet I need to introduce 2 lines that does not add up any other intersection point. Maybe you can use the points that are already present, letting it pass through one point and the other point which is also already present and the third point. So the way we arranged these ensures that all these 3 points are collinear because they were uniformly spaced, right? And therefore, a similar construction works for the other diagonal direction. Like this. You could see we are not inducing any other point of intersection. So already there were 9, now it's still 9. Yet we were able to introduce 2 extra lines. Therefore, you have the required configuration. Let's come to this configuration. 9 lines and 10 intersections. Particularly, I did not find it easy to come up with because you add one more line and one more point of intersection. It's not like adding 2 more points of intersection because 2 would be easier, but adding exactly 1 point of intersection with this will be a bit difficult to control. See, if you just plainly make like as many lines parallel, let's say 5 lines parallel and another 2 lines vertically parallel, we already got 10 intersections. Now, we need to introduce 2 more lines. At whatever 2 points you choose for constructing the extra lines, those extra lines, you will end up with a new point of intersection. So, it's kind of hard to abstract inducing a new point of intersection. So, after doing a lot of trial and error, I was actually able to come up with a triangular configuration, which probably we might be aware of. So let's take a triangle. So that means 3 lines intersecting to form a triangle. Then we take the midlines. What are midlines? Lines passing through midpoints of 2 sides. So there would be 3 such lines, right? So one through this midpoint and the other like this, and another like, okay, 1 second. And second one passing through this midpoint and the midpoint of the base, like this. And third one passing through the remaining 2 midpoints. Observe that these midlines will be parallel to the sides of the triangle. For example, the recently drawn one will be parallel to this side. Just by the basic proportionality theorem, they divide the sides in 1:1 ratio, the either side. Due to which, this red line and the base do not have a point of intersection. Therefore, we have only introduced 1, 2, 3, 4, 5 and 6 points of intersection till now. We have 4 remaining and we have 3 more lines remaining. So when you think of 4, a standard configuration comes into my mind, that is Schevians concurring in the interior of the triangle. So like this. Consider the 3 medians concurring. We know the point of concurrency will be the centroid. So what are the 4 points we are trying to introduce? Well, one is of course the point of concurrency, which is the centroid, and the other 3 are the intersection with the midlines. So you will generate 4 more extra points of intersection, thereby adding up to 10 intersections as required. So once you play around with these configurations that you already dealt with in some problem solving, you might be able to come up with this idea. And I think this is just purely pattern recognition. So you just keep on doing some trial and error and try to get it. But you do not need to follow any particular formula or theorem to solve this. And in that sense, I'm quite impressed with this question in particular for this year's RMO. Thank you for watching, everyone. Please put your ideas and suggestions in the comments. We will interact with you in that way. Thank you for watching. Bye.